Hi everyone, I am Kerem from the Cooling Systems Department of Dynamics PRC, the racing team of Polytechnic of Milan. Each year, we design and build a Formula-style vehicle to compete against other universities in international events. Today, I will present our motor thermal model developed in Simulink. First, let's start with the fundamentals. What are electric motors? They are machines converting electrical power into mechanical power for various applications, including propulsion. Different types of motors exist differentiated by their working principles and internal structures. They generate heat during their operation due to magnetic and mechanical losses, making temperature monitoring and thermal analysis critical for performance and safety in their industries of operation. How about our application? In our case, we use liquid-cooled permanent magnet synchronous motors to propel our high-performance Formula Student vehicle. These motors, one per wheel, dissipate substantial heat due to varying operational loads and environmental conditions. To address this, we developed a detailed thermal model in Simulink, later to be integrated with other components of the cooling system for a complete thermal simulation. What are the objectives of this thermal model? First, maximizing the performance of the vehicle by exploiting the motor's thermal characteristics. Second, determining the specifications of cooling required from other components of the cooling system and the motor's effect of them. Third, keeping the motor in a safe operation range and preventing adjacent components from thermal damage. And lastly, improving the overall design by identifying bottlenecks. Then, let's talk about our model. The model is a 6 degree of freedom representation of a PMSM built in Simulink. We have used Simulink instead of SimScape to have a faster model that can be integrated with live telemetry and simulations. Internal motor components are simplified into material layers, which can be seen in the figures. This simplification is augmented by the data extracted from CAD software to account for the motor's intricate 3D geometry. Alongside other components, stator and rotor heat capacities also include the structures found in their cavities, such as copper coils, epoxies, and magnets. To introduce the heat dissipation by losses in real time with accuracy, we use motor power loss datasheets for stator losses and rotor losses. Then, between each component and the ambient, heat transfer takes place. For realistic heat transfer coefficients, they are calculated directly by the temperature differences, material properties, and if the medium is fluid, for characteristics. For the model's workflow, we have a set of inputs, the model, and the outputs. For inputs, we have the data from CAD softwares, the material properties, and the motor inputs. Then the model computes these parameters to output the temperature values of its internal components. The model also accepts telemetry data for validation against real-world sensor readings from the vehicle's performance runs. Here you can see this thermal circuit of our motor, which is replicated in our Simulink model. The 6 degrees of freedom temperatures can be distinguished by their thermal capacitances. We have the shaft, rotor, stator, housing, liquid, and upright. As noticeable from the circuit, at the stator and rotor, the losses are introduced by the power dissipations. Between each of these components, depending on the case, contact conductions, internal conduction, gas convection, and liquid convection takes place. The motor mainly cools down by transferring its heat to the liquid water flow pumped across the channels. At both ends, we have the grounds, which are the gearbox where the shaft is mounted, and the ambient which surrounds the upright. And with these grounds, we prevent any inaccurate accumulation of temperature inside the components. Let's take a look at our model in Simulink. As you see, the model consists of the inputs to the model and the outputs. For the inputs, the model can be fed by either user-defined values or by lookup tables created from telemetry readings. Then the model processes these inputs, conducts its combination, and outputs the temperature values of the components into a scope and also MATLAB for further investigations. The model is a continuous model operating with the concept of integrating temperature change rates over time starting from the initial conditions. The liquid is pumped across the cooling channels during the motor's operation, so its temperature changes aren't integrated but rather given out directly to the following members of the cooling system when combined with other thermal models. You can see the heat interaction subsystems within each layer. For example, from housing to the liquid, first the corresponding heat transfer coefficients are calculated, in this case forced fluid convection and internal conduction, then the total thermal resistances, and then the heat flux between housing and liquid. Before arriving at the temperature change rates, the heat capacity of each component is calculated. For example, for the stator, as can be seen, the heat capacity of the solid part, the epoxy in its cavities, and the copper coils in its cavities are accounted for. Then, these heat fluxes and heat capacities are fed into each component subsystems to calculate the temperature changes between each of its adjacent layers dynamically. Specifically, for the rotor and stator, additional heat dissipations are introduced by using three-dimensional lookup tables based on datasheets of motor speed, motor load, and stator temperature for power loss values. For these lookup tables motor load input, a MATLAB function is integrated to find the motor load by the given motor torque speed characteristic curve for different stator temperatures. In the end, all these temperature change rates are summed up to result in the total temperature change of the component for that time instant and then integrated over time. To compare the model with the real case, we resorted to the telemetry data from our vehicle acquired during competitive events last summer. Before comparison, firstly, here you can see the simulated temperatures of each component from the shaft to the upright of the motor. Then, the simulated stator temperature from the Simulink model is compared with real-life temperature sensor readings taken from its stator. This validation underscores the model's capability in capturing complex three-dimensional heat transfer dynamics. Ongoing enhancements involve cross-verification with controlled test bench experiments using alternative motor configurations. In conclusion, our Simulink-based thermal model provides a robust framework for analyzing and optimizing electric motor performance under dynamic conditions. This capability not only enhances vehicle performance but also informs system-level cooling strategies for improved reliability and efficiency. Thank you.